Today we are going to do section 4.2, which is on page 352. Now this is, what is that? This is the limits and continuity section of the 2D, of the function of two variables. Now the function of two variables are absolutely the same as the function of one variable when it comes to stuff like limits and things. The only difference is now instead of just one dimension, you have to think about two dimensions. That's the only difference. Otherwise, everything works out exactly the same. First, let's consider the definition of a limit itself. Okay, what's the limit? As you can see, the limit is defined exactly the same as the limit definition in calculus 1 for the 1D function, whereas the limit of f of x is equal to L if there exists, well, this is just a 1D definition, right? If for every epsilon bigger than 0, there exists a delta bigger than 0 such that if x minus a is less than delta but not 0, then for all x, then f of x minus L and it is what? Okay, the book has a slight mistake here. Okay, it does not read bigger than epsilon. It's less than epsilon. I mean, after all, it's approaching it. Why would it be bigger? That doesn't make any sense. It's less than epsilon. That caught me. I didn't notice that when I was prepping. But anyway, yeah, small mistake, no big deal, right? It's less than epsilon, obviously. So then, so we extend this to the 2D definition. So then the neighborhood now is a circle or something. It's called, the book calls it a delta disk. I don't remember calling it that. It's just around a 2D neighborhood, which in this case, in 1D, the neighborhood is just a line segment. In 2D is, I guess you can call it a circle. But the idea is the same, right? A delta disk is something that's within a circle of that dot, as you can see in the book here, right? And that is our neighborhood, but the principle is exactly the same. That is, within that neighborhood, and whether it is 1D or 2D, you have to define the limit in, let's look at the next page. Okay, the limit definition reads exactly like the previous limit definition. That is, the limit approaches L if there for each epsilon bigger than 0, there exists a small enough delta such that for all the points that's inside the delta disk, and not considering the point itself, because we're only talking about the limit. Whenever you talk about the limit, you don't care about the point. You just care about its neighborhood. What are the neighbors doing? Okay, and if all the neighbors are doing something, that's good. The point itself may or may not be there. We don't care. Okay, the point may not even exist. We don't care about that either. So we're asking about the guy's neighbors. So then, what are the neighbors doing? The value of f is no more than delta from L. That is the limit, it's less than, f of x minus L is less than epsilon for all the stuff that's inside the delta disk. Okay, so anyway, so that's exact same definition. And so then you and then with that said, being that the definition is exactly the same, limit laws are also exactly the same. Let's look at theorem 4.1 on the next page, okay? A big pack of laws, and let's look at them real quick. And the constant law, which says the limit of a constant is the constant itself. Identity law, limit of x is just limit of x equal to a. Limit of x as the x and y both approach a and b is just a, because you don't care where y goes in that limit, right? Just x. And similarly for b. And the sum law, the sum of the limit is you just add them up individually, and same as difference, multiplying by a constant, same thing. You can pull the constant in and out of that limit. The product law, same thing. You can do the limit of individuals or multiply them together. The quotient law, the same thing. And power law, the same thing, right? You can just calculate the limit inside or outside the power, the power of the thing, the exponent. And And similarly, the root law, same principle. You can calculate the limit of the root inside or outside, and it all comes out the same. Just like it feels like we're back in calculus 1, okay? Except that we have one more variable. Otherwise, everything's exactly the same. So look at the example 4.8, which you will do for your homework. You have to calculate the limit of these two things. Yeah, and they come out very readily by following the limit signs, which actually just means you're going to evaluate it, right? So please do example 4.8 as part of your homework. And well, yeah, see, the book wrote a ton of stuff. See how much stuff there is? And well, that's only, theoretical. In reality, we don't write any of that stuff. You just plug it in and everything will come out. That's all you have to do, right? Yeah, I think so. And of course, now that we have done the easy limit, the next thing is the immediate question is what happens if the limit doesn't exist? Then you do the same thing as you've always done, okay? Now, the example 4.9, go ahead and look at that yourself and figure out why it doesn't exist, probably because the denominator is 0 or something like that. Anyway, so let's flip over and look at and wow. Well, your page sure goes on and on why it doesn't exist, but well, whatever, you look at that, okay? And sometimes it's because you're dividing by 0, but other times it's because of some other reason. Well, whatever. Sometimes, because in 2D, what happens is the limit to a point might not be the same. That is, it might, the graph might have a tear in it that somehow, because it's not continuous. So if the graph has a tear in it, then what happens is this. All right, here's some random piece of paper, and you pretend that that is the surface. All right, now look at the middle. Now, if the graph is going happily, but somehow there's a tear in there, then the limit at that tear does not exist, because the limit by definition means it has all the neighbors along the tear has to be in the same spot, and they're not. See, along the tear, okay, I tilt it so you can see a little better. Along the tear, some of the neighbors on one side and the other neighbors on the other side, right, of the giant chasm. So when that happens, then the limit doesn't exist. And yeah, and some graphs have tears because they probably divide by 0 or some other reason. Anyway, so when that happens, you have a limit does not exist situation going on, which is no big deal. Just go ahead and figure out when it doesn't exist, and then do the math. Which then your book seems to do a lot of math for that, but I don't think that's probably necessary. You should be able to crank that out rather real fast. At least not that many pages. Anyway, next let's go to page 358, okay, and we will consider interior points and boundary points. So what is an interior point? An interior point is something where there is you find a point in the domain or some region of something, some area, and then yeah, so let's and once you find a point, and then if you can find a small neighborhood, okay, that it can be a large neighborhood, but as long as you can find a small neighborhood where every single person in the neighborhood belong to the function, I mean belong to the set, okay, right now we're not talking about function, just a set. So if all the neighbors belong to the set, then this is called an interior point. And then what's not an interior point is if you have a boundary point. That is, a point is a boundary point if every neighborhood, okay, draw a circle, an open neighborhood around it contains points from both sides, and that would be my tear would be a great example. Now, if you consider the tear, right, the point along that edge of the tear, then its neighbors, and the neighbors are considering just the x coordinate, okay? Its immediate neighbor, if you draw a small circle, the guys who live right along the edge will have neighbors on the top cliff and neighbors from the bottom cliff. As long as he doesn't mind jumping. And so assuming he doesn't mind jumping, there are neighbors that he can jump to, that are very, very close. No matter how close you draw him, if he lives along the direct edge of the tear, right, he will always have neighbors on both sides. Well, pretend that he's a grasshopper or something, so jumping's okay for him. So going to the next page, let's look at some definitions that are somewhat important. As odd as they might sound, well, for now, they actually sound fairly obvious. So let's look at the first definition. S is called an open set, okay? If every point of S is an interior point, that is, every point inside S, you can find a neighborhood that is completely inside S. And then S is called a closed set if it contains all the boundary points. Now notice that in that case, the open and closed are not exclusive of each other, like the word might imply. Something can be open, neither open nor closed. In fact, some things can even be both open and closed. But that we will worry about that later. My point is that you just determine each set whether it's open or whether it is closed. It's that simple. Now let's keep looking. And then an open set is a connected set if it cannot be represented as the union of two disjoint non-empty open sets. So an open set is connected if it's one glob, right? There's no two distinct globs of it. And then a set is called a region is if it is open, connected, and not empty. Okay, so some nice open connected set, not something broken up in a bunch of chunks, and it's all open, so there's nothing weird happening, so relatively speaking. And then a set is called a region. And let's move on. And next definition, what is that? Is now if something on the boundary, then well, the limit, what happens to when you look for a limit of something on the boundary of the definition? Well, you do it the same as you do any other way. Okay, it makes no difference if it's on the boundary. If it's on the boundary, then you only consider x as x approaches the point from within the set itself. The approach from the other side is not considered. In other words, this limit, for example, exists, right? This limit, well, normally it doesn't exist because if you're approaching from both sides, then the limit doesn't exist. But if they ask you, well, I only want the limit from one side only. It's sort of like the one-sided limit in one dimension, same principle. If they say, well, I just want the limit from, over here. I don't care about the part where it fell off the cliff. Then in that case, the one-sided limit does exist. So that's what they mean by when you're calculating a limit on the boundary. But otherwise, you do it exactly the same way. What is that? Now, where am I? Okay, got it. So then limit of a function on the boundary, example 4.10. Please do that as part of your homework. And then the next thing we're going to do is something called continuity, a very familiar concept. And it is because we're going to repeat exactly what we said in Calculus 1. What is continuous? Continuity is defined by three conditions. Number one, the function has to exist at the point we mentioned. Number two, the limit, the function has to also exist. Number three, the limit has to equal the value of the function itself at that point, which is a repeat of Calculus 1. So let's move on. And please do example 4.11, which is a complete repeat of what you did before, except there's one more variable, but it doesn't really make that much difference. Okay, so do that. And we will go to the next one. Various theorems. Okay, the sum of continuous functions is continuous. The product of continuous functions is continuous. Next. What happened? All right, the composition of the continuous function is continuous. All right, yeah, whatever. Then so please do example 4.12 as part of the homework. And lastly, I think we are going to talk about function of 3 or more variables. What about them? Nothing. that everything works the same way. In 3 dimensions, now in 2 dimensions, we call it the delta neighborhood. The book calls it a delta disk. In 3D, it's called a delta ball. But otherwise, it works exactly the same. Of course, what happens in 4D? Then we don't have a name for it. So there's no reason to call it disk, ball, whatever. We call it, normally, we just call it the neighborhood, okay? And then we don't care how many dimensions it has. But the idea is exactly the same. If there's a delta ball, then it has well, it's just a small area around the point with the radius delta. It's a ball. And I guess for higher dimensions, your book calls it a delta ball as well, because you can't think of anything else to call it. Of course. And what else would you call it anyway? Anyway, and it doesn't matter how many dimensions there is. You do everything exactly the same, and which is just the same thing as you did in Calculus 1, except you consider do all 3 variables. Yeah, it's slightly longer, not a lot though. So please do example 4.13 as part of your homework. And with that, we have come to the end of this section. For homework, please do, let's see. Okay, I can see it now. Let's see, I'm not going to type the homework under the video for a while because I'm changing equipment and trying a different way that might be more efficient. So for homework, please do, what is that? Page 354, examples 4.8, 4.9, 10, 11, 12, 13. And then for the homework on page 366, please do problems 65, 71, 77, 83, 87. And for 87, just plot the graph in 3D. And then, I don't know, the answer will come to you or something. And 93, 95, and 101. We're still at the stage where introducing the concepts. So everything sounds kind of simple, right? I mean, similar to, maybe not simple because it's still rather tedious. When you have too many dimensions, then you got a lot of work. Right? It's like a guy who married multiple wives. He has to provide for all of them, and it's a lot of work. But the principle is the same, right? It just, there's no real difference. So you do it the same way as if you did it with 1D, and get them all done. And then after that, we will do derivatives, I believe, and things will get a little more exciting. All right?